All right, my name is Ben Christensen. I'm a student in Dr. Delacorte's Physics 106 class, and I will be presenting about electric current. So what is electric current? Current, represented by the letter I, is the rate at which charge flows through a conductor. So that rate is equal to the change in charge, or Q, over the change in time. And to help us understand that a little bit better, we have this example here off to the right of water flowing through a pipe. Like electric current, water flowing through a pipe has a rate at which it flows through that pipe, and it also has a direction in which it flows through that pipe. A certain number of molecules pass through a certain area of pipe over a certain period of time. And that's just like current. Current then is measured in charge per time period, and the SI unit for that is amperes, which is equal to coulombs, a measure of charge, per second, measure of time. So I mentioned just now that current also has a direction. The direction of current is the direction a positive charge moves. And this is an easy way to help us know what direction the current is moving in different situations with positively charged and negatively charged particles. In the example on the lower left, positively charged particles are moving to the right, so the current is also moving to the right. In the example on the bottom right, negatively charged particles are moving to the right, so therefore the current is moving to the left, because that's the direction that the net positive charge is moving. If negative charges are moving to the right, then they're leaving a net positive to the left, and so that's going to be the direction that the current is moving in that situation. So how does current travel? So current or charged particles moving through a conductor need energy to make them move. We're not in static equilibrium here, where charges aren't moving, charges are moving. And so what provides that energy is the electric field inside the conductor. Normally in static equilibrium, we don't see an electric field inside the conductor, but with current, when charges are moving, we do. And so the force that is causing those charges to move is the electromotive force, and that's the Coulomb force, the force between these charged particles. As one particle moves, it causes the other particles near it to also move, and can represent that force by those two formulas there. With the electric field then, a helpful thing to remember is that the electric field lines are going to be pointing in the same direction as the current is flowing, from positive to negative, or the direction that a positive charge would be moving. So to make this a little bit more concrete, here's an example of that we can use to equate charges moving through a conductor and how that happens. So we've got this tube here, which is white with all these green balls inside it. And they're pretty closely packed in there, so you can see as soon as one ball moves into the tube, another ball is going to get pushed out. That one ball moving in is going to push all the other balls in front of it. And this is a really good example of how current propagates. And it does so really, really fast. As soon as one charged particle moves within the conductor, all the others near it are going to be affected by that Coulomb force and are also going to move. And this is sort of like through this conductor, it's like an electrical shock wave. And that electrical signal moves really fast, a third the speed of light, 10 to the 8th meters per second. Despite this really fast propagation of current, the actual forward velocity of an individual charge, or the drift velocity, is really slow, only about 1/10 of a millimeter per second. And that's because, as you can see down on the bottom, there is a net forward velocity of that electron moving around in that conductor, but you can see it's bouncing all around, bumping into different other particles as it slowly makes its way forward. And so with drift velocity, this gives us another way to conceptualize current. Like we've said, it's the rate of the flow of charge. And so we can use this second formula to help us understand current even further. Current is equal to the density of charges within a conductor times the amount of charge carried by each of those charged particles times the area that they're moving through times the velocity that they're moving through that area with. And so again, that gives us current, which is the movement of charge through a certain area over a certain amount of time. So now that we understand current, this can help us understand another couple of important concepts about electricity. And the first one is resistance. Resistance is the impedance of current. Current's trying to flow through this conductor, and that flow of current, those charged particles, are going to be resisted. They're going to be bouncing into other charged particles, into the atoms that make up the conductor, and that's going to prevent their overall path forward. And so impedance, or the resistance, or the level of impedance of the current, is measured in ohms. And in different materials have different levels of resistance due to material-specific resistivity. Different materials are better at resisting current than others. In addition, the shape of the conductor really matters for resistance. A longer conductor is going to have more resistance because there's more material for those charges to travel through. In addition, a thinner conductor is also going to have a higher resistance because there's a smaller area that those charges are all trying to squeeze through. And so with an understanding of current and an understanding of resistance, this brings us to a really important formula called Ohm's law, and that relates voltage, or the electric potential energy difference per unit charge, it's the separation of charge, is equal to the resistance of the conductor times the current flowing through the conductor. And so you can see in this circuit diagram that we have, the current is flowing counterclockwise there from positive to negative, the direction a positive charge would go. It's flowing through a resistor, that little squiggly line there at the bottom, and the flow of charge, the current, is caused by this voltage, this potential energy difference. And this formula is really useful for a lot of different situations, and we'll show one right now. So one really cool application of these concepts that we've been talking about is in neuroscience, is how the neurons in our brain or in our nervous system communicate with each other through electrical signals. And so there's about a 90 millivolt potential difference or voltage across a neuron cell membrane. And positively charged sodium ions are going to be flowing in to those neurons to then cause an electrical signal that's going to go down the neuron's axon and signal other neurons. And that sodium channel is super, super tiny. Because it's super skinny, it's going to have really high resistance. This example, we're going to say 3 times 10 to the 10th ohms. So what is the current in amperes that's flowing through that one sodium channel? And so then we can use Ohm's law to figure this out. We just plug those numbers in. We rearrange Ohm's law a little bit. So I equals V divided by R. And then plug the numbers for voltage and resistance in, and we get a current of 3 times 10 to the negative 12 amperes. And that's really tiny. With tons and tons of sodium channels, that gives our neurons the ability to send electrical signals and allows us to move and think and do all the other things we do. And thank you very much. That is current.